So let's get started with the presentations, continuing. So we're going to have Mariama and Lee talk about article topics and retweet networks. So it's a continuation of Joachim's data sets on UK elections.
Yeah, okay. So we wanted to look at the articles and article topics in this retweet network. So the idea is to do topic modeling on the articles from the web that were linked from Twitter. And then to connect this in the retweet network to see what kind of tweets different people are tweeting, and what kind of articles they are tweeting. So we don't look at the tweet content, but that's article content. So the steps for this was first to get the list of URLs that we want to get the articles from, then to actually get the articles, to extract features, so to turn them into something that we can feed into our machine learning algorithms, and clean up the data a bit, do the topic modeling, and then connect to the tweet network. And as you'll see as we go through our notebook, things took longer than we were maybe thinking from the beginning, so we have not been able to do everything that we set out to do. And one of these things was that we also had an idea that it would be really nice to try to summarize the articles in an automatic way, so that we would, and then we could do part 3, 4, and 5 with the summaries also, and with the articles, and then compare those results to see how good our summarization was working. And this turns out to be, I don't know, its own project or its own research project, and Mariama spent a lot of time trying to figure out the summarization, but unfortunately we didn't get it working. So, but if you're interested, you can ask her more about it. Okay, so the first step to get the list of URLs, as already mentioned, we used this UK election data that Joachim presented before. And then we want to filter out just the tweets that have URLs. And well, we should have done this on the whole data, but we started out with just 3%, a random sample of 3%. And at the end, we didn't have time to read on the whole data anyway, so this is the only results we will show you. To get the feeling for the numbers here, well, you don't need to look at all of this, but you can see here the ratio, no URLs, so there's 82% of the tweets don't have URLs, so it's not a very big percentage of them that have URLs. So in total, about 1 million tweets with URLs are in this data set, but the distinct ones are only about 270,000, and then we take only 3% of that, so we have about 8,000 URLs. And then I made a little test sample so that we can run these things. So that we can run part of the notebook. So after having this data frame with the URLs, then we want to get the article content.
Okay, so when we see an article, so usually you have like a lot of different sidebars. So you have the main content, and then so you have the main content of the article, which is the body that we want to extract. You have like probably images, and sometimes you also have like a lot of other layers that we want to remove from the HTML page. So for this part, we use a Goose library, which allows us to clean out completely the articles and then just extract the text. So I won't even run this actually. But then what we did is we kind of created like a class article. So then it will retrieve the body of the article, a short description of the article, the title of the article, and we can also add if there are like keywords, and so that's the main way we will describe each article. So we will have like at the end like a data frame that will contain all this information. So sometimes when we have like a URL, we can't find the article content. So in this case, we'll just put a keyword saying that couldn't find the articles or the not found stages, because then this will be important further out to kind of do the machine learning step afterwards. So there is also something which we often find is the shortened URL links. So we had to extend those ones, and then for this we used. So this, I mean, we kind of used a lot this mastering Spark for data science book. So they worked a lot on pulling data from the web and scrapping, and also how to handle the URL and how to store the data. So it was quite insightful for us to build this tool. So so
yes, so as an example, these 13 links that I pulled above, this is what we will get after running our web scraping. So you get the title, body, and you know, the first example doesn't even have a body, so it didn't work really as we wanted. But then here you see one article that has body. We also get the domain, and if there was description or keywords, we get that as well. And then we have this status. If we had some problems or exceptions, we will get not found, and this is something that we will filter. For example, here there's one that's not found, so we will filter out these things. Yeah. So then we want to extract the features on this data and to clean it up a little bit. We save our 3% data frame to Parquet so that we can easily look at it now. Because, well, we did it 1% at a time, and getting 1% already took about 30 minutes. So this was not a very quick scalable thing, but there is some options that we didn't really follow, but you can try to look into to make it quicker. And one thing we did do was, for example, this goose allows you to also get the images from the web pages, and we didn't ask for that, and I think that already sped it up a little bit, but it was still a bit slow. Okay, so then we have this data frame, and we want to filter out, like we said, this keyword that we put with not found if we had some problems. And then we also want to filter out things that we know are not articles. And we know, for example, that if it comes from YouTube or Vimeo, then it's a video, or it's not an article with text content, which we want. And from Twitter, it's usually like people retweeting, so it's other tweets, it's not really articles, so we also want to get rid of this. And this is, of course, something that if we had done before getting the content, it would also speed it up, because then we would be looking at less URLs, but we also didn't figure out the way to do this easily, so we filter them out afterwards. And then we want to start building the features for the machine learning, and we do this using the Spark inbuilt functions. So we use this regex tokenizer to split the text into the words, and then we remove stop words using the stop words remover, and here you see what our code looks like. And for the stop words remover, we give it an array of words that we want to get rid of, which we basically use the same that we had in class when we did the LDA, I think. So the stop words are words that are not very meaningful, like add, or they don't really say much about what the text is about, so we remove them. And then we transform this with this count vectorizer into a vector of word frequencies for each document. So then we have our feature vector that we can feed into our machine learning, and we want to do topic modeling with unsupervised learning. And the first one of them we did is this latent hearsay allocation, and we already talked about this in class. but in case you don't remember it very well, I think this figure is quite insightful on how it works. So it's basically a model where every document, so every text that we got from the URLs, is modeled as belonging to several topics, and then the topics are basically a distribution over words, which is inferred from the whole collection of documents that we have. Let's see if I can go back.
Just the one to the left.
This one? Yes. Okay, and then, so with this LDA, you infer the topics and the topic distributions, and then you can see the probability or the amount of each topic that is in each document as well. And then we also wanted to do k-means, which is another kind of unsupervised clustering algorithm that we also already heard about and also did in class. And then Mariama will talk about that a little bit more. Okay, so we use, again, the built-in machine learning things in Spark. And so we tried just running this LDA on our stuff. Yeah, so this is the code showing how to fit the model. And then we want to get the topics, which is the model gives you in this way. And with some transformations, we can get it in a nice way that you can then visualize in D3. And we use, this is just the same code as we had in the this class's LDA. And when you look at this, I think one of the first things you notice is there's a lot of small words that do not seem to be English. We didn't check our articles beforehand, so when we got here, we noticed that, yeah, we have a lot of articles that are not in English, which are kind of being identified in different topics, but this was not really what we wanted to do in the first place. So then we figured out that we need to clean the articles, clean our data set again. Yeah.
Basically, one topic was Spanish articles.
Yeah, I think
French.
it's French. I think it's mixed French and Spanish.
It's Latin languages.
And then you have some, for some reason, German and Italian, and I don't know why this ended up together. But yeah, so we figured out we needed to clean our data set better. And also, when doing this, we started noticing that we had some articles that were not really articles, but kind of messages about cookies or enabling JavaScript, those things like this. And the brute force way that we figured out so that if you try to get any kind of results, we're kind of just to filter these things. So you see this is a mess.
Get rid of Italian and some more French.
Yeah. So of course, to make this so that you could use it like with another collection of documents, you need to do this more carefully to really filter out the languages. I did notice, for example, that we had one article where there was a quote for it was the English article with a French book title or something. So if we just filter out on normal French words, we might get rid of these kind of things, which we would actually not want to. But so this works for our data set, but maybe not for other ones, and we're not sure it really removes everything. It's still, even after this, we have like 5,000 articles, so of course we have not looked at each one to see that they are actually good articles. Also, from this big thing, we noticed that there were some words that we think are not very informative about the topics, so we wanted to add some more, to remove some more stop words, like, for example, set appears in several topics. You see the green one, this purple one, it's down here too. So it's in a lot of the topics and it doesn't really tell you much about what the topic is. So we removed some more words. And here you can see the whole list of stop words that would be interesting. Then we run everything again, and I have put this just with the title, but the whole code is there, but it's just the same thing again. And then we get a new one. And this looks a bit better.
Yeah, I'm sure President Trump will be happy, right? It's bigger and better than everything else.
But I still feel like it's not easy to say that the topics are about something in specific. It feels quite mixed.
The question is,
Cookies, potatoes, and refugees.
is the color the topic?
Yes, so the
Okay.
different colors.
And the
are
keyword
different
is,
topics.
yeah, okay.
And then these are the five most
frequent.
important, most frequent words in that topic.
Okay.
And then now here we have 7 topics before we have 10. But so there are several things that we could and we should do to try to get like good results out of it. Try different parameters like the different number of topics, the number of iterations. We just use the default minimization algorithm in LVA, and I know there's at least 2 that are supported, so we could try different ones and see if we get similar results or which one gives the better results. We haven't done this because we have not had time. But still, if we would go from this result, this tells you the topics, but then you might want to look at the topic probabilities for each of the documents. So then you need to transform your feature vector or data frame. And then we get something with a result with a vector, which is the probabilities for each topic. And then this was the way we figured out how to get this information. So here you have, for example, the probability for topic 0 for all the articles in our data frame that have at least 0.9 probability of being in topic 0, and then with the topic probability. So in this way you can, at least if your different topics make sense, then you can filter on the articles that belong to a certain topic. And and this will give you some information. So the other way we wanted to look at was this k-means clustering.
Yeah, so in this case, I mean, the idea is still the same. So we have like a lot of articles, and then we still want to see, I mean, what is the global, I mean, are many articles talking about the same things, or are there different articles, or is it like all random articles? And then, as we've seen before, we have clearly some topics. So, for example, we have President Trump, and so like somewhere Golden Gate, which connects quite well in the same group. So in this case, we did k-mean clustering, so we did also a bit of cleaning. It's also ugly, so I won't show it. But so we cleaned a bit everything which wasn't English word, because it counts a lot when you do this vector representation of the bodies. So we removed all this, and then we use the same tokenizer pipeline and remove stop words as well. So I just rerun it because I filtered a bit more to get the k-means. So we have something slightly different in this case. So for the k-means, it's the same thing. We also use this ML, the k-mean algorithm provided by the ML lib. So we do an iterative process for the k-mean, and then we selected a small tolerance threshold. So we started with 10 clusters, because it's quite hard when we have too many clusters, and then we don't have so many singletons, so then it's probably okay if we have like a small cluster numbers. So so this is just based on the count vectors, so it's term frequency, which is used for the features in the k-mean in this case. So here it's for each cluster the number of like members. So we see that we have like a predominant cluster which contains mostly random. I mean, it contains everything, but we could still isolate some topics. And then it wasn't so clear, but then we could still get some. Yeah, but I guess I would have to. I think I put it exactly. So then So it's a bit diverse in the clusters, which one is called 0, but then we could still find some trends a bit. So all the articles talking about taxes, care, or like people, politics, they all ended up in the same clusters. We had like a cluster about Trump plus Russia, US politics globally, and we had like also a clear cluster about climate change, ecology, and like the different meetings about it. And we could, if we compare this a bit to what we got for the LDA, we see that it's not really like so comparable. So we're comparing the number of articles in each cluster and the total number of topics. I mean, you could still have like an article with many topics, but then we could still try to link if there are like many articles on a topic. Yeah, exactly. So we could still try to link. I mean, this could be I don't know how to say it, but then we could still be sure that, for example, over this like 3,000 articles, they have like many of the topics over here, but then we see that the numbers are not really like you don't have so small like members for each like topic. That's all.
This is not really a comparison like a one-to-one. We don't expect the same thing. It was just kind of a, well, we can do this with both, and we can kind of look at if they seem to agree. But I realized now that the LDA that I sorted here was actually with only 7 topics, but the k-means was with 10. So you see that obviously there's several things that are not really the same.
It's a bit tricky. I mean, finding the number of clusters is a bit complicated. So in the book we've been reading, so they said that the sweet spot for the number of clusters when you have like a large data set could be around like 300 or some lower or more values. But then in our case, I mean, since it was still linked to the elections, we assume that most of the articles will deal with kind of the same content. It's an assumption. So it's not a really cool clustering. So what we try to do is to normalize a bit the vectors or the features. So the first one was just using the term frequencies, but then if we use the approach which is called inverse document frequencies, we can kind of it's a bit like this when we remove stop words, it's words which are not so meaningful. So with this approach, we will kind of like reduce the impact of words which are quite spread out or which are often seen. And then we did a bit of, we normalize also just to have an even vectors. And in this case, we get like a kind of better clustering. So we see clear, so we still have like a big cluster, of course, but then now it's more spread. So we have like we already started separating articles, and we still find again like a cluster with like US politics and economics, and it's quite isolated from other topics. And yeah, so we can go on. So this is still a bit manual work. So then we have to see what is the content of each cluster. And so there's another approach to describe the text body, which is using hash vectors. So it's similar to the count vector. I mean, the goal is similar as the count vector, but then in this case, everybody will be described by a hash vectors, which like describe the full feature of this body. And then we did similar things. So we normalized it using the IDF approach. And in this case, it's similar still. I mean, using this IDF allows us to be really more accurate with the description of a body. So we get better feature vectors, and then here we separate quite well the full corpus we had. So now we are also able to separate what is happening in the UK and what's happening in the US. So we still have like a big cluster. This is something we need to try to split in a way, and then it didn't really work by increasing the number of cluster we created. It was still this one, which was the biggest cluster, like a few thousand. So it's probably we need to find a way to describe better the bodies. So here we could find a cluster which was really talking only about London attacks and what happened in Manchester, and we still found Trump, US politics, and Trump Russia. It's always in the same cluster. So we could kind of describe, we could kind of split well all this database of URL, but we still need to work a lot on this cluster 0, which is 3,000 articles. So
yeah, so the idea was to connect this to the tweet network, but as you saw, our clusters are not very meaningful and don't really say much, so we didn't really spend much time in trying to get this to the tweet network, since we don't think it can provide much information and there's still lots of work to be done. But we did do a quick look, and the kinds of results that we will get, so the data frame where we have the URLs, we have the body, so the whole article text, and then we have the predictions from LDA, which are here called just topic, and the predictions from the RK means, and this one is the one with the count vectorizer and the TF-IDF. So if we have this meaningful topics in these two columns, then we can connect a URL and the post and the user to the different topics to see what they have been talking. And as just one example, we tried to check what we would get for Jeremy Corbyn, and it turns out that we just have one article that he has tweeted, and then we could check in which clusters it would be. So if the whole thing was working, then you could do this in the whole data set and for different people and kind of see it on top of the tweet network to see what they are talking about. Okay, and that's it.
Yeah, so here the idea would be you can improve and refine these things so that you can have a news network with its own cluster of topics that's essentially embedded in the URLs of the retweet network, right? Yeah, and one thing I just realized when you were talking is, when we watched the talk by the LDA guy, the recent talk he gave in Scotland, I think. So he was talking about these extensions of LDA, where they were doing LDA with recommendation engines, where he's combining both methods. I'll have to do more work. I'm wondering, if you can take the information in the retweet network, which could be these pairwise distances, however you want to project that, and then maybe use that as a prior or something to inform the LDA itself. That's possible, I think.
So based on similarity.
Yeah, because they do some kind of recommendation thing, and they combine LDA with recommender systems, because in their problem, the recommender systems have this cold start problem. But in general, what I would be nice is to use the retweet network as a prior, and do some LDA with this prior information. Do you have a question?
Yes, or maybe a remark. Yeah, just first of all, it's really nice to see sort of the intermediate things that didn't work as well. Yeah, sometimes these things are very interesting. So just maybe I was thinking maybe it would have been easier to initially, when you got the URLs, look at the domain name, because you can probably filter out foreign domain names by just looking at top level. So if you remove all .fr and .es and whatever, you can probably get rid of most of the French and German and Spanish things. And maybe it would have been easier to just restrict to domain names where you had at least, 50 links to this, because then you get rid of weird small sites that are probably maybe just spam, and then you can also get rid of. So you can actually look at the top 100 and see which of these are newspapers and which of these are like YouTube or something. And then maybe this would have been an easier way to. I mean, this is easier to see in retrospect, but.
But we did a bit of domain filtering, but then full domains and not really only like the .fr.st or because I mean you could still be a French website and still have .org, .com, or so. Yeah, but it's probably.
I think maybe if one restricts to look at the top 100 domains or something, because I suspect that a lot of them are probably linked to British newspapers, or the interesting ones are probably linked to British newspapers. So maybe take the top 100 and then filter these manually or something.
That's quite cool. Yeah.
I don't know, maybe you too.
Yeah, I thought a little bit about these things, but at some point I was thinking about what do we mean with an article? Is it really just news articles and then we could filter around like newspaper sites, or do we want like all kinds of blog posts and they could be even smaller blogs that maybe don't have so many links to it that might still be interesting? So I think one of the ways to filter out things that we obviously don't want might also filter out things that we maybe want and we're not sure on.
I mean, it's false positives. It's tricky.
Again, just something, now that you mention it, I think if one has the HTML source, one can probably identify blogs, because blogs run on a sort of fairly small set of software types. So you can maybe you can actually identify what blogging software it runs on. Because I think there are probably just 3 or 4 blogging softwares that 95% on. So if you can identify WordPress, you have most blogs, I think.
That's what we use the scraper to do with, like it looks at the HTML content and then just gives us the text.
Yeah.
So it doesn't have a built-in thing to do this. And it's
I
a library that we're not going to touch, but maybe, I mean, it was on GitHub, so you probably could.
I think you probably can look at, because it also has to download the HTML at some point. So you can probably, I don't know, but I suspect that with WordPress or something, there's probably some line that somewhere that will only appear on WordPress sites. Exactly, something like this. Yeah. And then you can probably identify WordPress, and then you probably have at least half the blog posts.
Yeah, but usually it's hidden for security reasons. Most of the websites they hide the platforms they use, so it's more difficult to hack. But small websites probably don't do that, but at least big websites they would usually hide.
Yeah, but big websites aren't a problem because then you already have a lot of links to them, so they are in the sort of top 100 domains or something.
And what happened to the other thing, Adam's what is it called? The scalable k-means thing where he's projecting these pairwise distances from the.
Yeah, so he did a bit of embedding. So first, like, so they kind of describe like the body of like a vector length, which is like billions, like a huge one. And then they did a bit of embedding to reduce.
So the random projections based on.
Exactly. So this we couldn't really implement it because then there is no like it's like implementing it. So it was a bit short.
No, I'm not saying you've done a lot on this. I'll try to do that. So that's the RDD based thing we were looking at yesterday.
Exactly. So, but
because that's supposed to scale to the Gmail data or whatever.
But then, first it was still quite fast, and then what we did is we used, so for the vector length, we used the vocabulary size, and it was it's tens of thousands, so it's not so big. But then, in their case, they were streaming, and then they had a lot of data, and here we still had 3% data. But then we could still do this if we have like a bigger vocabulary and bigger database.
The bottleneck is really downloading all the articles rather than the analysis, I guess.
Yeah, if you want to implement this in some kind of streaming part, or then, for us, it was mostly that we didn't have time to work more on this.
Yeah.
I mean, while the articles are downloading, you can be doing something else, looking at some of the other things.
I mean, sort of the time it takes running the statistical
takes
part is very small, would be my
compared
guess,
to-
compared to the data.
Yeah, but then you download once, so and then you save it in archive
Yeah,
files.
at least if we have, I mean, if we're looking at this data set, like getting the full data set instead of the 3%, it would take time, but it's something that you would do once, and then you could do all the analysis several times and change. So
I mean, the thing that
it's not impossible.
Andrew Morgan, right, who talked to all of us, so it's chapters from his work. So when I was in Dublin, they presented this thing, the K-means clustering of the entire world's news GDEL data set, right? That's 99 point something percent of the whole world, every language machine translated by Google. So, and then what you saw is these stories developing, they were finding duplicates, and so every couple of days, a new story will come, and most attention will be on it, and another one, and so on. So our sort of idea was to take Joachim's British election data and then look at the URLs like you've done, go through this, and somehow merge it with that streaming GDEL thing, so we can see in the global storylines that are emerging what's happening to our particular set of users we are tracking in Twitter. Like, where do they map to that global news storyline, right? Which is all doable. It just means master's thesis works. Good. Are there any more questions? Lee and Mariam? Okay, let's give them a hand again. So we have next speakers. Do you want to go next? Yeah.